How bones, fascia, and movement build lifelong vitality. 1. The philosophy of biotensegrity. For decades, medical science described the human body like a skyscraper, bones stacked upon bones, stabilized by the pull of muscle. Modern biomechanics offers a more integrated model, biotensegrity, biological tension integrity. In this framework, bones function as compression elements within a continuous tension network of fascia, ligaments, and muscle. Rather than acting as isolated levers, skeletal elements distribute forces through a dynamic web of connective tissue. Structural integrity depends on balance within this system. If tension is excessive or insufficient, load distribution changes, joint stress increases, and tissue resilience declines. True structural health therefore requires attention to both. The mineralized matrix, bone. The collagenous network, fascia and connective tissue. Levin, 2002. 2. The hard frame, how to build strong bones. Bone is not static. It is metabolically active and constantly remodeled in response to hormonal, nutritional, and mechanical signals. On acidity and bone. Blood pH in healthy individuals is tightly regulated. Normal dietary variation does not meaningfully acidify the bloodstream. However, chronic metabolic acidosis, as seen in kidney disease or severe metabolic dysfunction, can increase bone resorption. Bone health is therefore influenced less by dietary acidity and more by adequate mineral availability, hormonal balance, mechanical loading, inflammation status. The calcium question, synergy over isolation. Calcium alone is insufficient to optimize bone mineralization. Bone formation depends on coordinated nutrient and hormonal signaling. 1. Calcium, structural mineral, provides compressive strength. Found in sardines, with bones, dairy, leafy greens, and sesame seeds. 2. Vitamin K2, regulatory cofactor, activates osteocalcin, a protein involved in binding calcium to bone matrix. Observational research suggests K2 may support proper calcium utilization and may be associated with reduced vascular calcification risk, Maresh, 2015, though vascular health is multifactorial. 3. Magnesium, metabolic support, required for vitamin D metabolism and involved in bone crystal formation, Nutrients, 2013. These nutrients function within broader systems that include vitamin D status, parathyroid hormone regulation, and mechanical strain. The piezoelectric effect and mechanotransduction. Bone exhibits piezoelectric properties. Mechanical strain generates small electrical potentials within the crystalline matrix. However, electrical signaling is only part of the story. Bone remodeling also depends on strain magnitude, fluid shear stress within bone, cellular mechanotransduction pathways, mechanical loading, particularly intermittent, higher impact or resistance-based loading, stimulates osteoblast activity and bone formation, Thompson et al., 2012. Nutrition provides materials. Mechanical loading provides instruction. Three, the fluid web, fascia for strength and flexibility. Fascia is a three-dimensional connective tissue network composed primarily of collagen, elastin, proteoglycans, and water. It is richly innervated and plays a major role in proprioception and force transmission, Bordoni and Mahabadi, 2020. Thixotropy and tissue viscosity. Facial ground substance demonstrates thixotropic properties. It becomes more fluid with movement and more viscous during prolonged immobility, Klingler et al., 2014. Movement influences hydration and viscosity of this matrix, which may affect tissue glide and perceived stiffness. Glycine and collagen synthesis. Collagen synthesis requires adequate amino acids, including glycine, proline, and lysine. Glycine represents a large proportion of collagen structure. In individuals with sufficient total protein intake, glycine deficiency is uncommon. However, collagen-rich foods may support connective tissue turnover, particularly during aging, injury recovery, or increased mechanical demand. Razak et al., 2017. 4. The Food Encyclopedia. Ranked by nutrient density and structural relevance. Tier 1, the Seed Matrix, mineral-dense plant sources. Seeds are mineral and nutrient-dense and provide beneficial fatty acids. They contain phytic acid, which may modestly reduce mineral absorption in diets heavily reliant on grains and legumes. Soaking or sprouting may reduce phytic acid content, though the effect is most relevant in diets heavily reliant on grains and legumes. Ulbricht et al., 2009. Rank. Food. Structural contribution. 1. Black sesame. Calcium and copper, supports collagen cross-linking. 2. Chia seeds. Fiber and hydrophilic compounds that retain water. 3. Pumpkin seeds. Magnesium source. 4. Flax seeds. Alpha-linolenic acid, ALA. 5. Hemp seeds. Complete amino acid profile. Tier 2, regulatory and collagen-supporting foods. Muscle meat provides essential amino acids and supports overall protein intake. Connective tissues, however, are relatively richer in collagen-specific amino acids. Rank. Food. Structural contribution. 1. Natto. Significant dietary source of -7 Malawian kwachas, vitamin K2. 2. Beef tendon. Rich in type 1 collagen. 3. Chicken feet. Collagen, chondroitin-containing tissues. 4. Bone broth. Provides gelatin and glycosaminoglycan components, concentration varies by preparation. Consolidated the key players. Nutrient. Primary source. Structural role. Vitamin K2. Natto, fermented dairy. Supports proper calcium utilization in bone tissue. Silica. Bamboo shoots. May support fibroblast activity and type 1 collagen synthesis, complementary to adequate protein and vitamin C intake. Glycine. Beef tendon, gelatin. Major structural amino acid in collagen. Magnesium. Pumpkin seeds. Supports vitamin D metabolism and contributes to bone mineral balance. '5. The movement signal, how exercise shapes your bones and fascia. Mechanotransduction describes how cells convert mechanical forces into biochemical responses. 5.1 Bone adaptation. Intermittent loading, resistance training, impact activity, incline hiking, produces strain patterns associated with bone remodeling. Low impact, repetitive movement, e.g., flat treadmill walking, supports general health but may produce smaller osteogenic stimulus compared to progressive resistance training. 5.2 Facial adaptation. Fascia responds to tensile load, compression, multi-planar movement, variability of strain, movement in multiple planes, rotation, lateral bending, reaching, may promote tissue variability and adaptability compared to strictly linear movement. The distinction between bone and fascia adaptation is key. Bone adaptation is particularly sensitive to strain magnitude and rate, whereas facial tissues appear especially responsive to variability of direction, duration, and multi-planar loading. Six, integrated food priorities. Rather than a single, master switch, structural health emerges from coordinated nutrient availability. Category A, mineral and regulatory support. 1. Natto, vitamin K2, -7 Malawian kwachas. 2. Black sesame, calcium and copper. 3. Chia seeds, fiber and trace minerals. 4. Pumpkin seeds, magnesium. 5. Sardines, calcium, vitamin D, omega-3. Category B, collagen and tissue integrity. 1. Beef tendon, type 1 collagen. 2. Chicken feet, collagen-rich tissue. 3. Bamboo shoots, silica, orthosilicic acid precursor, provides dietary silica, which is absorbed primarily as orthosilicic acid, the bioavailable form associated with stimulation of fibroblasts and support of type I collagen synthesis. Evidence suggests a supportive role in connective tissue and bone health, likely complementary to adequate protein and vitamin C intake rather than a primary driver. 4. Camu, vitamin C, required for collagen hydroxylation. 7. Structural stressors. Advanced glycation end products. Age's chronic hyperglycemia promotes non-enzymatic glycation of collagen, increasing stiffness and reducing elasticity, particularly relevant in diabetes. Highly imbalanced mineral intake. Excessive sodium can increase urinary calcium excretion, though the effect is moderate and context-dependent. Prolonged sedentary behavior. Extended immobility is associated with increased stiffness and reduced tissue variability. Regular movement breaks support musculoskeletal health. Excessive refined sugar intake contributes to systemic inflammation and glycation-related tissue changes. Circadian disruption and sleep deprivation. Bone remodeling follows a circadian rhythm. Deep sleep supports nocturnal growth hormone and melatonin surges, which contribute to bone turnover and collagen repair. Chronic sleep restriction, late-night light exposure, and irregular sleep schedules may impair optimal remodeling and recovery. '8. The Master Protocol, Applied Integration. Morning, hydration plus fiber plus vitamin C, e.g., chia with citrus, promotes hydration and supplies vitamin C, which is required for collagen synthesis. Midday, mineral-rich meal, sardines, greens, seeds. Afternoon, brief resistance or impact stimulus, 5 to 10 minutes, variable intensity. Evening, protein-rich meal including collagen-containing foods before bed, gentle multiplanar mobility work. This protocol emphasizes integration. Nutrients provide material. Loading provides signal. Recovery enables hormonal integration and tissue remodeling. '9. Structural synthesis, the four pillars of human architecture. Structural integrity is not the result of a single nutrient, exercise, or intervention. It emerges from coordinated biological systems operating across material, mechanical, and temporal dimensions. The living human frame depends on four interacting pillars. 1. Material. Nutrition. Minerals provide compressive strength. Amino acids provide tensile structure. Cofactors regulate placement and synthesis. 2. Signal. Mechanical load. Bones and connective tissues adapt to strain. Without sufficient loading, remodeling slows regardless of nutrient availability. 3. Timing. Circadian biology. Bone turnover, collagen repair, and hormonal signaling follow daily rhythms. Deep sleep provides endocrine conditions that favor repair and rebuilding. 4. Recovery and variability. Movement plus rest. Multiplanar movement maintains tissue adaptability and hydration. Periods of rest allow integration and remodeling. When these four pillars align, structure becomes adaptive rather than degenerative. Longevity is about maintaining a responsive architecture that can distribute force, absorb stress, and regenerate across decades. Longevity, therefore, is not merely about density or flexibility, it is about maintaining a responsive architecture that can distribute force, absorb stress, and regenerate across decades. The structural secret is integration. References.